Alrighty, now we have the final video of the three that I'm making for this year's final exam, 2025. This one is on learning targets 16 and 17, where 16 is about integrals using area and Riemann sums, and then 17 is about integrals using the fundamental theorem of calculus. So let's jump in. So this first one is like the last couple videos. This is from a checkpoint, specifically checkpoint 5, where we're given a graph of f of x and we need to use it to compute the following. So we have three definite integrals they want us to solve. And as a reminder, when you're given a function, f of x, and a definite integral, like the integral is effectively the area under the curve. Geometrically, that's what it's asking. So we're given this function here, or a graph of this function, and integral bounds, and it basically tells us to find the area. So for this first one, we need to find the bounds or the integral from 0 to 3. So I'll just mark that here. This one's actually pretty simple. We can almost just count it out in terms of boxes. So each box is 1 by 1. So this is 1, 2, 3, 4, 5, 6. And then this is half a box here and half a box here. So that makes 7. Easy enough. Now we go from 3 to 7. And right away, I can see that this box or this triangle is the same as this triangle. And since one of them is above the x-axis, one of them is below, the one below is negative and the one above is positive, they cancel out, and that's 0. And finally, from 7 to 9, we have 1, 2, 3, 4. And then this is some part of a box, and this is another part of the box. But just based on symmetry, we know that all of this would be 2. So, and we have half of that. So this right here is 1. So this gives us 5 total. Okay, now we have another function on a graph, and we need to compute L sub 3, which is left-hand approximation, Riemann sum, for definite integral from 0 to 3, and it tells us to construct 3 rectangles using the left endpoints. So since we have L3, and we have a width of 3 from 0 to 3, we know that each box will be 1 wide. This will be pretty easy to set up. So L3, I'm going to look at it's a left-hand approximation. I'm going to look at the left side first for our first box. So starting at x equals 0, go here. That's our first box there. For the next box, similar on the left side, we'll have at x equals 1, start here to make our box, and then back to here for the left side. So we have a constant width of 1 because this is 1, this is 1, and this is 1. And we add up the heights. So we have 3 plus 4 plus 3 of our rectangles. And this is just equal to 10. Easy as that. So yeah, this checkpoint, I think I did pretty well on it from what I remember seeing. But yeah, not too bad. Now let's jump in a little bit more specific questions. This one is about the fundamental theorem of calculus, and part A wants us to use part 1 of the fundamental theorem of calculus to find the following. So we have here a derivative of an integral. And typically derivatives cancel out integrals because integrals are antiderivatives. But in this case, we have a function in the integral bounds. So we can't just go about crossing out the derivative and the integral. We have to consider the function of the bounds in the chain rule. But what I'm going to do first is I'm going to rewrite this as negative d dx because we have the function as a bottom bound, and I'd like it to be the top bound. So from 3 to tangent of x. And then just rewriting 5t e t squared dt. Now we're going to plug in. We'll have negative 5. So instead of t, we need to plug in our tangent of x. And then e to the t squared, where t is tangent of x, so tangent of x squared. But since we are inputting a function from the integral bounds, we need to use the chain rule. And the derivative of tangent is secant squared of x. And that's our answer using part 1 of the fundamental theorem of calculus. You pretty much are just plugging in the integral bound instead of, if that was just x, you just plug x right into t, and the derivative of x is 1. But in this case, it's tangent that we're using as the bound, so we need to consider the chain rule. Now we're asked to use part 2 of the fundamental theorem of calculus to solve some definite integrals. So similar to here, we have a greater number on the bottom of the integral bound and a lesser number on top. So I want to switch that around. I'm going to rewrite this as integral from 1 to 4 of x squared plus x to the 1/2, because that's the same as square root of x. This is a little easier for the power rule. And I forgot that negative. I was just talking about that. I forgot that negative, but there we go. Okay. Now, evaluating antiderivatives, we have x cubed over 3. And then plus 2/3 x to 3/2 using that power rule. This is from 1 to 4. Alrighty. Keeping mind of that negative, I'm just going to keep that on the outside for now. And plugging in 4, we have 4 cubed over 3 plus 2/3, 4 to the 3/2, minus, now plugging in 1 cubed over 3 plus 2/3, 1 to the 3/2. Okay, simplifying even more. 4 cubed, 4 times 4 is 16, times 4 is 64, so 64/3. And then 4 to the 3/2 is equal to the square root of 4 cubed. And square root of 4 is 2 cubed, which is equal to 8, times 2/3 equals 16 over 3. So plus 16 over 3 for that term there, and then minus 1/3. I'm subtracting another 2/3. And that just comes from distributing this negative. Okay. Now we're pretty much done. I mean, every denominator is 3. That makes it pretty easy. 64 plus 16, that's 80. Minus a 1 and then a 2. We have negative 77 over 3. All right, trig here. Negative cosecant of x times cotangent of x. Looks pretty gnarly. I'm not seeing immediately like a good way to use power rule or u substitution, but once I studied my trig integrals, I realized that this is the derivative of cosecant. So I can write this as cosecant of x, considering those integral bounds, pi over 2, pi over 6. Or sorry, I said it's the derivative. Yes. The derivative of cosecant of x is negative cosecant of x times cotangent of x. So the antiderivative of negative cosecant of x times cotangent of x is cosecant of x. And I know that cosecant of x is the same as 1 over sine of x. So I'll have 1 over sine pi over 2 minus 1 over sine pi over 6. And sine of pi over 2 is just 1, so 1 over 1 minus 1 over sine of pi over 6, that's 1/2. This is the same as 1 over, or sorry, this is the same as 1 minus 2, which is -1. Also not so bad. Yeah, part 2 of FTC is just definite integrals. It's just take the antiderivative, being mindful of your signs, I would say. Remembering that like when you have an upper and a lower bound, you're going to be subtracting those two. And if like the upper bound is a smaller number than the lower bound, which you have here, then you got to bring that negative out in front. Okay, on to the next. More of a word problem here, golf ball production. It looks like we're going to be looking at the area method here. We have that Titleist manufactures the Pro V1 and Pro V1X golf balls at varying rates throughout the year. So with this rates being non-continuous, we will need to analyze graphical data to estimate how many golf balls are being produced during given months. The y-axis represents the monthly production of golf balls in thousands of golf balls per month, and the x-axis, which I guess is the same as the t-axis because we're considering time, will be measured in months. And we are asked how many golf balls in thousands are produced at the end of April. So if we had t equals 1, that's the end of January, 2 is February, 3 is March, so 4 is April. So we'll consider through the end of April here, number 4. And we're given that the y-axis is the rate of golf ball production, the rate. And what happens when we integrate a rate is we get the total production, because like the derivative of production would be in terms of time. So it'd be like a d production over dt. By integrating that, you just get production. So if we find the area, because area is the antiderivative or area is the integral, then we just get total production. So we should find the area here. In terms of shapes, I mean, I could consider this a trapezoid. I don't really want to. I don't have that equation necessarily memorized. I'm going to consider a triangle and then 2 rectangles. Easy enough. So this will be 1/2 times the base, which is 2, times the height, which is 4, and that just equals 4. For this one here, we have a width of 2 and a height of 4. That's equal to 8. This one has a width of 4 and a height of 2, so also equal to 8. So golf balls produced, we have 8 plus 8 plus 4. Remember, it's in thousand, so all we need to write is 20. That's how many golf balls, 20,000 golf balls will produce at the end of April. Now we need to consider the entire year. So we have that 20 in mind. I would say let's just split this up and again into shapes. Actually use a different color. So we have a triangle here, a rectangle here, and another rectangle here. This will be 1/2, but the base is 3 this time, and the height is also 3. So 9/2, which is the same as 4.5. This one has a width of 2 and a height of 6, so equals 12. And this one has a width of 6 and a height of 3, which is equal to 18. Okay, so considering the 20 from before, I have the 20, I have the new 18, the new 12, and that 4.5 from the triangle. And this gives me 54.4. Easy as that. So it's 54,500 golf balls produced throughout the entire year by Titleist. Okay, continuing on this same example, we have that quality control engineers used AI and data to create a better model for the production rate. Seen in the figure below, it's one smooth function, one smooth curve where the axes are the same. So we're using Riemann sums here, L3 and R3. And it's a little note to round the production rate to the nearest half thousand, which is the same as like a tick mark on there. It's like this is half thousand, this is half thousand, this is half thousand. Easy enough. I'll show you what I mean in a bit. Okay, left Riemann sum with 3 subintervals. So delta t will be 12 minus 0. That's our total width. 3 subintervals. That tells us 4 months is the width of each. 4 months, 4 months, 4 months. Okay. Starting out, on the left Riemann sum, we'll look at t equals 0. It did not fit at all. Okay, this is our first one. And a height of 2. Now, at t equals 4, still on the left side, we'll go to 8. And to show you what I mean, this is pretty close to this tick mark right here, which corresponds to 5.5. And then at 8, that's where we're at right there, which is 6. Okay, left Riemann sum. We know that our interval width is 4. And now we just add up our heights. So 2 plus 5.5 plus 6. In a sense, I'm coming out to 54. 54,000 golf balls produced throughout the year. I'm going to clear this real quick for our right Riemann sum, where subintervals will be the exact same. So at 4, and at 8, and at 12, but right Riemann sum, so we get our values from the right side of each rectangle. So going all the way up to here. And that occurs at 5.5, which is the same 5.5 that we saw earlier. And then for the next one, we'll also see it occurs at 6 once I round it. So that's no coincidence. You know, the left Riemann or the right Riemann sum, the second rectangle would be the same. I'm sorry, the left Riemann sum of the second rectangle would be the same as the right of the first. So this is at 6 here. And then finally 12, we go up to there. And that is at 3. Okay, so same subinterval width of 4. Now we add up our heights of 5.5 and 6 and 3. And this comes out to 58. So a little bit of a disparity in terms of the left Riemann sum with the right Riemann sum, but you see how generally this inaccurate this would be, especially for this curve. The left Riemann sum and right Riemann sum of only 3 subintervals is nowhere near enough for like an actual representation, because you have all this space here that's incorrect, all this big gap here. It looks like it may actually come out so that it equals out, but that's just purely coincidence. But we will see in the last question, fundamental theorem of calculus method, we will actually use the real model. The model for production rate in part B, which is this part here, this curve, is represented numerically by this function here, this rate. So to find the actual total production, as I said before, we can integrate that rate. And we're doing it over the whole year, which means we want to solve integral from 0 to 12 of that RT function in terms of t. All right, so let's consider our antiderivative. We'll have negative 7 over 72 times 1 over 3 t cubed, and then 5 over 4 times 1/2 t squared, plus 2t. This is happening from 0 to 12. Now, little tip, I have t in all of these terms here. I have 0 as this lower bound. That means I'll be plugging in 0 to this t, and 0 to that t, and 0 to that t. All three of those terms, and 0 plugged in multiplied by anything is 0. So I'm not even going to consider that. I'm just be wasting my time, wasting my breath, so I'm not going to do that. I'm only going to consider that 12 upper bound, which is of negative 7 over 3 times 72 times 12 cubed plus 5 over 4 times 1/2, so we'll call it 5 over 8 t squared, 12 squared, plus 2 times 12. And as I said, you can use a calculator for this one. The exam questions will be written in a way that you won't really need a calculator, or you wouldn't need a calculator. I didn't necessarily have the foresight making these questions to have it be super easy to calculate by hand, but no matter, the answer is 58. Now, you may be seeing, like in the previous problem, we also got 58 for this right-Riemann sum. That is purely coincidence. This is by no means telling you that a right-Riemann sum will be incredibly accurate and be able to model this complex function. As you can see, there's a whole lot of error throughout. It's just purely coincidental that those, I guess, boxes above and below the curve equal out. So there's no takeaway there to be made. I think if anything, the biggest takeaway is that Riemann sums are inherently a little bit inaccurate, but as you increase the number of subintervals and I guess decrease each subinterval width, it'll be more accurate. But then in this method, using the fundamental theorem of calculus, we get an exact answer because we can analytically find the antiderivative and thus find the total production of golf balls. I guess looking back as a quick summary for learning target 16 and 17, we used area to calculate definite integrals. We used Riemann sums. We used part one of the fundamental theorem of calculus, like recognizing how to handle functions and integral bounds. We used definite integral, or we solved definite integrals using part two of the fundamental theorem of calculus, recognizing whether you need to use a power rule or recognizing trig. This is sort of like an overarching question here with this golf ball production one. We used area, we used two different types of Riemann sums, and then ultimately the fundamental theorem of calculus to get an exact answer. I think that just about covers it for the exam extra help videos. I hope they were useful. It seemed like those three topics, the related rates, the optimization, and then this integral stuff, was the most requested by the class. So that's why I went with these three. Apologies if your interest wasn't chosen. But regardless of whether this was something you thought you needed help with or not, I think these would be all pretty useful. Get ready for the exam. And with that being said, I wish you the best of luck on the exam. You'll do great. Just practice hard, study hard, and there'll be no issue at all. Yeah, good luck.